The next topic's integration, which was developed when mathematicians hundreds of years ago were posing the question, how do we find the area under a curve? So if you remember from differential calculus, the question they were posing there was, how do we find, so we've got a curve like that, how do we find the gradient of a curve? They could find the gradient of a straight line. That was easy, we've got a formula. Curve's a little different, purely because it's a curve. So remember, we took the point closer and closer and closer and closer, and that's how first principles was developed and deriving. So then they were posing the question, well, how do we find the area under a curve? We can find the area of rectangles and trapezia and all sorts of other 2D shapes, but what about under a curve? So the first thing they did was took a curve on a Cartesian plane, y and x, and I'm just going to do one just as a general one, and they were looking between points A and B on the x-axis. How would I find the area of that curve? So they used what they knew. What did they know? They knew how to find the area of rectangles. So they thought, if we divide this particular area under here up into a number of rectangles, maybe we could approximate the area. So they divided it into one large rectangle. Right, so what they did was something like that, and they found the area in here. So they times the x difference here by the height, and if you think about that, that's f of a and f of b. Alright, that's fine, but there's a whole lot of area there that is not included, so that's obviously a very, very inapproximate area. So if I rub that out, let me start again. Then they thought, right, what about if we take from the highest point up here, what about if we go out the other way and we take this rectangle? Okay, we get the area of all of that from A to B, length times the width. But again, well, all that area there is superfluous. We don't need that one. So again, not exactly a real approximation. So then they were sitting there, no TV, whoops, no TV, lots of books I suppose, definitely no internet, so they had plenty of time on their hands. So they went back to the same curve. They said, right, it's between A and B, one rectangle's not going to suffice, so how about we divide into two? So we go there and there. So if you think about that, well, the area now that's not included is smaller, definitely. And if I rub that out and we go the other way and we do the outer rectangles, that's the area, and we take there and there, again, that area that's superfluous is smaller than the first one. So still not exactly, but a little better than the first approximation. And then you guessed it, what do? Yep, they divided it into three rectangles. They kept going. So there's A and there's B. But now we're going to go into three rectangles. 1, 2, 3. All right, well, the area seems to be getting smaller in these little extra bits. If we rub it out and we do the outer limits, there and there and there, and the areas that's left over is a little bit less. So you can see what it's leading to. They discovered that if they took a very, very large number of rectangles, that the leftover area was smaller and smaller and smaller as the number of rectangles got bigger. So, and the one we saw in class the other day on the computer, I think we went up to 100 rectangles. So if I took the lower limit of the area, which are these, we're just chopping off a little bit at the top. You see, if I try and colour these in now. Well, obviously all these little pink bits, much smaller, so that's a lot closer than the first approximation. If I do the larger rectangles and come out, it's going to be the same. So those pink bits on the outside are a lot smaller, and clearly the more rectangles I take, the smaller the number of little bits left outside. So you can see we're approximating a limit. And so what they said was that if I add up all the rectangles, so if I sum the rectangles and I sum those areas, I'll get pretty close to the area, the more rectangles I take. Well, let's have a think about what is the area of one of those rectangles. Say we've got that. So that's f of A, and that's f of B, or the y value, isn't it? So we know that the area of a rectangle is the length by the width. Well, if we call the bottom the width, what they said was we're just going to call that delta x. Whatever value of x, it's going to be constant. Each one they divided up, it was a constant width. So we're going to call that delta x. And the height, well, the height doesn't matter which, if you take the smaller rectangles or the larger rectangles, it's still going to be a difference. So if we take the smaller rectangles, the height is f of A, or the y value, isn't it? If we took the larger rectangles, it would be f of B. But let's go with f of A for the moment. So the area equals the length, the height, which is f of A, times by the width, which is delta x. Okay, and if we replace that A with the x value, whatever x value it is, so it's f of x times delta x. So that's what they set up here. It's the sum of the rectangles where the height, or the width of it, is f of x, and we're going to multiply that by delta x, which is the constant width across the bottom. So as you can see, when they were looking at integration, they're looking at taking a limit. If you think about it, the first one we took, the delta x was quite large. If we divide that same area into 2, it's going to be half the size it was. And clearly the more rectangles you take between those 2 points of interest, let's say we really divide it up, then that delta x is going to be very small. So over time, the delta x is approaching 0, and that's a limit. And that's what we want. We want these rectangles to be as extremely thin as we possibly can. So the area then was written as a limit equals as delta x approaches 0, and it was a limit of the sum of the rectangles. Add them all up, that's going to sum it, which we saw was f of x, and I'm going to change the, well, I won't change it at the moment, times, so f of x was the height or the length, and the width is delta x. Now over time, over lots and lots of problem solving and probably hundreds of years, the terminology changed a little bit. The limit was dropped, so the area now we write as, so the sigma sign is stretched out. They probably just got sick of writing it perfectly, so they were rushing, they stretched it out, and it's f of x dot, and the delta changed to a d, between the limits, whatever limits we want. So that's the terminology for integration. And the theory behind it is it's a limit of the sum of the rectangles, and there's specific algebraic means with which to calculate it. And there's also 2 approximate methods we use first, which are not the exact area, but we'll do those next lesson.